glycogen synthesis and degradation. Today, I will tell you about the regulation of glycogen synthesis and degradation and the disease associated with glycogen metabolism. Okay? Before you start, I want someone to remind me from yesterday's lecture, what is the most important enzyme in glycogen synthesis? Most important enzyme. Glycogen synthase, excellent. Okay. And when is this enzyme active? During the fed state or during fasting? Okay. So did you get the idea of when do we store glycogen and when do we degrade glycogen? Okay, who can remind me what is the whole idea about storing glycogen and degrading glycogen and why it's stored and what is degraded from yesterday's lecture? Yes.
It's stored when we don't eat.
First of all, what is glycogen?
It's a stored form from glucose.
Okay, why we need glucose?
To energy.
Okay, so what are the two most important needs for glucose?
For brain and muscle.
Okay, so we need blood glucose to maintain, blood glucose homeostasis for many cells, including the brain and the red blood cells. Okay, so these, especially the red blood cells and the brain, need a continuous supply of glucose. Okay, that's why we need to maintain glucose homeostasis. And which organ will help to maintain glucose homeostasis? The liver. Okay? And why also we need glucose? What is the second important reason why we need glucose? For the muscles. Okay? So we need to maintain blood glucose to keep our cells working. Most importantly, the brain and the red blood cells. And we need a continuous supply of glucose for the muscle. Okay? What are the two sources of glucose or the three sources of glucose?
Diet.
So diet is the exogenous. Okay, the endogenous source of glucose.
The breaking of the glucose.
Okay, so when we are not eating, where will the glucose coming from to maintain the blood sugar and to maintain? Okay, so we store glucose as glycogen in the liver and in the muscle. The one in the liver is stored to maintain the blood sugar, the blood glucose homeostasis. The one in the muscle is stored for the muscle only. Okay? So we said the muscles are selfish. They store glucose as glycogen for their own use. The liver is like a caring mother. It stores glucose for the whole body to maintain the blood sugar. Okay? So we have the well-fed state when we are eating, and we have the fasting when we are not eating. What are the two hormones which are important in blood sugar regulation? Insulin and glucagon. And please do not confuse glucagon with glycogen. Okay? Some students, especially the Arabic-speaking students, they confuse glucagon, which is a hormone, with the glycogen, which is the storage form of glucose. Okay? So, glucagon will be released when we're fasting.
Yeah.
Okay. And what is the function of glucagon?
Break down glycogen.
Will it try to bring the sugar up or bring the sugar down?
Bring the sugar up.
Okay, so it wants to prevent hypoglycemia. So it wants to bring the sugar up. Insulin is secreted when? Okay, so when we are eating, the body will secrete insulin. And what is the function of insulin? Bring the blood sugar down. So these concepts need to be very clear in your mind. Don't try to memorize them. Just it's logic, you need to know them because they make sense. Okay, so today we're going to talk about the regulation of glycogen metabolism, and we talk about the disease associated with glycogen metabolism, and we call them glycogen storage diseases. Okay. So because, as we said, we need to maintain the blood glucose level, That's why we are going to control the synthesis and degradation of glycogen. Okay, so these synthesis and degradation are tightly regulated. They are regulated very well, tightly, يعني so firmly. Okay, so in the liver, glycogen synthesis will accelerate. What does accelerate mean? It will go fast or it will increase during the body. It's a long sentence, that's why I didn't want to post my lecture. So by the way, my lecture is not on Moodle, so I will just do final touch change and then I will post it, okay? So in the well-fed state, glycogen synthesis will accelerate, okay? It makes sense, okay? When you are eating, when you have an excess food, this is the time to store things, okay? It's like, if you cook too many big meals, you have a party, you cook too many big meals, this is the well-fed state, you decide to put some meal later in the freezer, right? So this is when you store things in the well-fed state. Okay, so glycogen synthesis will be fast in the well-fed state. In the skeletal muscle, glycogen degradation occurs during active exercise. Okay, so when we are exercising, this is when we need energy as a form of ATP, and where the energy will come from? Glucose. So this is when glycogen degradation will happen in the muscle. Okay, and when do glycogen synthesis occur in the muscle? When we are resting. Okay, so as soon as you stop moving, your muscles will start storing glycogen, provided you are eating. Right. So now we're going to talk about the details of the control of this glycogen synthesis and degradation. So we have two enzymes. The one that regulates synthesis, we call it synthase. So you can't have a better name for the glycogen synthesis enzyme. And the one that regulates glycogen degradation is the glycogen phosphorylase. Okay, as you learned yesterday. So these two enzymes are controlled by two mechanisms. We have the allosteric control, and we have the control by hormone, which is not allosteric, which is using cell signaling or signaling pathway. Right. What is allosteric? What does the word allosteric mean?
The substance bind to side either than the
Other.
side. Yeah.
Other than the active site. So you have a substance that binds to the enzyme at the site which is different than the active site and will make that enzyme more or less active. This is allosteric control. Okay? And then you have the hormonal control. So which hormone do you think will be involved in the regulation of glycogen synthesis and degradation? Insulin and glucagon. Okay? So they will not bind to the enzyme, that's why it's not allosteric control. They will bind to a receptor and they will start a cascade of events. So there is a series of events by activating a series of enzymes. So we have multiple steps before we reach the synthase and the phosphorylase, making it more or less active depending on the state. Okay? So allosteric is direct. You have a molecule like a glucose 6-phosphate. It will bind to the enzyme, either the synthase or the phosphorylase, at the site other than the active site, and it will make it more or less active. Very easy, one step. The hormonal control, so insulin or glucagon, will bind to the receptor. They will trigger a series of steps, and the final step will be the activation or the deactivation of the phosphorylase or the synthase. Okay? So why this hormonal regulation? What is the importance of hormonal regulation and why we have this multiple step? You will study again in Mol 2 cell signaling. But the importance of cell signaling and having a cascade of events in cell signaling, you need a small amount of hormones. So you only need a few molecules of insulin and glucagon, and because you have a cascade of events, then each time you are activating or you are controlling more and more molecules, so you are having like amplification of the effect. Okay, so this is the importance of cell signaling. You can amplify the effect using a small amount of hormone. Okay, so this regulation is complex, as you imagine, because we need to maintain our blood sugar, our life depends on it. So we have many enzymes, as we will see, that are involved in that regulation. We have many molecules, and also calcium in the muscle is going to be a regulator of these enzymes. Okay? Right. So we'll start first with allostatic regulation. So because we need the glucose for energy, so which molecule is going to regulate that the glycogen synthase and phosphorylase? Which molecules will indicate the level of energy in the cell? Two molecules, either glucose, and it's going to be glucose 6-phosphate in the muscle, okay, but in the liver it's going to be both glucose 6-phosphate and the liver, and the free glucose, okay, as we'll see in a minute. So glucose will signal the energy level. What is the other molecule that will signal a high energy level? Which molecule will signal a high energy level in the cell? ATP, thank you. And which molecule will signal a low energy level in the cell? AMP. Okay, so these three molecules, the glucose, or actually four, glucose 6-phosphate, ATP, and AMP. These four molecules are going to signal the energy level of the cell. They will tell us, how we're doing. Do we have enough, or we need to degrade more? And that's why they are the ones that are going to control the two enzymes, the synthase and the phosphorylase. Okay, and this is illustrated here. Okay, so it's exactly the same. Okay, except that here we have free glucose, and here we have AMP. Okay, so let us look at the liver first. Okay, what is the enzyme needed to make glycogen, we said? Glycogen synthase. Okay, so when do you think we need to make glycogen? When we are high in energy or low in energy? High. So when we have too much glucose 6-phosphate, this is when we are going to activate the synthase, right? By allostatic activation. When we don't have, so this is when we make glycogen. For glycogen degradation, what is the enzyme? Phosphorylase. Okay. So if we have too much energy, do we need to break glycogen? No. So too much ATP and too much glucose 6-phosphate will inhibit the phosphorylase, because we don't want to break more glycogen if we have enough, okay, of glucose, and if we have enough ATP. So if we have enough energy, we don't need to mobilize the stored glycogen. In the liver also, free glucose can inhibit the phosphorylase. And why we have this difference between the liver and the muscle regarding the glucose here? Why?
Because it cannot be degenerated in the muscle.
Okay, because we said that the muscle lack the phosphatase, and the muscle, they want to trap the glucose. So that's why, the energy is as glucose 6-phosphate. This is the energy for the muscle. But for the liver, we want to free that glucose. So even free glucose will be acting as and because we have the phosphatase, so this is, both molecules are the same for the liver. Okay? So this is regarding the liver. What about the muscle? We said it's the same scenario. So again, glucose 6-phosphate means we have enough energy. We are going to store it. Okay? And when we have enough energy, we don't need to make more energy, so we're not going to break. So we'll inactivate the phosphorylase. And also AMP in our muscle will signal a low energy state. It means we are running low on ATP. When we have high AMP, it means we're running low on ATP, so we need to break that glycogen. So this is allostatic control of glycogen metabolism. by energy level in the liver and in the muscle. Now we have all this text that talks about these figures, or this figure, which is from your book, talking about calcium. And this is the regulation in the muscle, okay? I'm sure you learned in your physiology about, when your muscle contract, what will happen to calcium? Okay, where is calcium released from? Sarcoplasmic reticulum. Okay, so you know more than me in physiology. Okay, so calcium is released, and calcium will bind. So this released calcium during activity will bind to a protein, which is one of a member of a family of calcium binding protein, which is the calmodulin. Okay, so calmodulin, have you heard of calmodulin before?
Yes.
Okay, so what do you know about calmodulin? Okay. Okay, so you studied this before?
Yes.
Okay. So calcium has 4 binding sites. It's going to bind to calmodulin and will activate this calmodulin calcium complex. I don't know if you studied up to here in physiology in MSK. Did you know about the enzymes? They mentioned okay.
Yeah.
They mentioned, yes? Kinase. Which kinase? Okay, that's something else. So this calcium will activate the calmodulin calcium complex, and this will bind to and activate, as we will see later, an enzyme called phosphorylase kinase. What is this phosphorylase kinase? It is the enzyme. It is the enzyme that will activate the phosphorylase. Okay? As we will see in a minute. But for now, just remember that calcium, by binding to its binding protein calmodulin and forming this active complex, is going to activate the enzyme, which is the phosphorylase kinase, which is needed to be active in order to phosphorylate the phosphorylase. Okay, so this enzyme, the phosphorylase kinase, will phosphorylate the phosphorylase, okay, making it active. And when the phosphorylase is active, what is going to do the phosphorylase?
Phosphorylation.
What this is the phosphorylase that will do what? Break down glycogen. Okay? I will repeat. Okay, so the calcium will bind to the calmodulin, making this calcium calmodulin complex. Okay? And it's going to activate the phosphorylase kinase. Okay? Why we need this enzyme to be active? Because it's going to phosphorylate the glycogen phosphorylase. And for the glycogen phosphorylase to work, it needs to be phosphorylated. So once this glycogen phosphorylase has a phosphate group on it, it will become active, and therefore what will happen? It will break down glycogen. It makes sense, because when you're exercising, the muscle will release this calcium. It means that the muscle is active. We need ATP. Okay, so this urgent need of ATP is going to trigger that activation, okay, of the phosphorylase kinase to make the enzyme, the most important enzyme for glycogen degradation, active. Okay, so all of that is written here. It's summarized in here. So what's this enzyme here? You add a note to know. This is the phosphorylase kinase. What does it do? It will activate
The enzyme.
glycogen phosphorylase. Okay? So by adding a phosphate group. Okay? So this is regarding calcium. We mentioned AMP. So when we have too much AMP, what does it mean?
We have less ATP.
Yes, so this is actually in the muscle under extreme condition of anoxia and ATP depletion. This is under heavy exercise. The AMP level will go up. Okay? So we don't have enough oxygen, we don't have ATP. So the AMP will bind to the phosphorylase and making it active. So this is allosteric regulation again, because it's going to bind and will make it active even without phosphorylation, because we don't have time to phosphorylate, okay? Because we are in desperate need of energy. Okay, now we're going to talk about the degradation by cyclic AMP directed pathway. This is the hormonal control, okay? And this is all actually summarized in here. So this is the cascade of events that I'm going to talk to you about. Let us talk about glucagon. So when we are not eating, our blood sugar goes down, right? Glucagon will go up, and the mission of glucagon is to bring that blood sugar up, right? So it is time to make or break glycogen? Break glycogen. So we need to break glycogen. Let us talk about the story in the liver. So what will happen? Because we want to raise that blood sugar to stay alive, right? So the glucagon, this is in green, the glucagon will bind to its receptor, its membrane receptor, and will trigger a cascade of events until we reach the final enzyme, which is the phosphorylase. Okay, so the phosphorylase A. So we have two forms of phosphorylase. We have the A form, which is the active, it's easy to remember, A active, and the B, which is inactive. Okay, it turns out that the phosphorylase is active when it is phosphorylated. It's easy to remember, phosphorylase, it's active when it is phosphorylated. So we want to reach to this stage. We want to phosphorylate the phosphorylase to make it active in order to break glycogen. But we cannot reach it in one step, so we have multiple steps. Let us take a few moments to understand these steps, okay? So what is the first step? This is what you probably have learned in other blocks. What is the first step here? You need to activate the adenyl, yes, so you need to activate the G protein that are going to activate what? The adenyl cyclase in order to make what? Cyclic AMP, okay? So now cyclic AMP will act as a secondary messenger because now it's going to carry the message that glucagon is bringing. Break that glycogen, okay? But glucagon will not enter inside the cell. It will bind to its receptor, activate the G proteins, which are going to activate the adenyl cyclase, which are going to make cyclic AMP. Now cyclic AMP will carry that signal. You know, glucagon is here, we need to break glycogen. What will the cyclic AMP do first? You should know this from your blocks. It will activate what? Yes, it will activate protein kinase A, okay? So cyclic AMP will activate protein kinase A. Once protein kinase A is active, what is it going to activate?
The calcium.
No, this is not calcium, okay? So this is different from the calcium story, okay? So this enzyme, when it's active, the protein kinase A is going to activate this enzyme. What is this enzyme? The phosphorylase kinase, okay? So the phosphorylase kinase, is it active when it is phosphorylated or no? Yes, you see here, phosphorylated P is active, okay? So the protein kinase A will add phosphate group to the phosphorylase kinase, making it active. Okay, so this is the enzyme I was telling you about, that calcium can activate this enzyme, okay, the phosphorylase kinase. So calcium will immediately activate the phosphorylase kinase. The glucagon, no, it needs to bind to its receptor, activate the G protein need to activate adenyl cyclase, cyclic AMP need to activate protein kinase A, then protein kinase A will activate the phosphorylase kinase. And from there, it's the same thing, okay? Once we have that phosphorylase kinase active, what is it going to do?
Phosphorylate the phosphorylase.
Yes, it will phosphorylate the phosphorylase, okay? Making it active. And now what will happen? We have breakdown of glycogen. glucagon يا حبيبتي صار لنا ساعة عم نحكي. Okay, it will break down glycogen. glycogen. Okay, glucagon is a hormone. Okay, glucagon, hormone, they run together. Okay?
Glycogen phosphorylase kinase A phosphorylates glycogen phosphorylase.
Yes, so this enzyme is going to phosphorylate. It will add a phosphate group, so it will phosphorylate the phosphorylase. This enzyme will phosphorylate the phosphorylase, making it active. Okay? So you need to have it clear in your mind. So glucagon, I repeat, bind to its receptor, activate the G protein, activate the adenylyl cyclase, which will activate the protein kinase A. Protein kinase A will activate the glycogen phosphorylase kinase by adding a phosphate group to it. Now this enzyme will phosphorylate the phosphorylase, making it active, and now we have glycogen degradation. So why we need all these steps?
Increasing
Increase the signal. We have only few glucagon, but each time, like we have, let's say we have 4 glucagon, they will activate, let's say, maybe 10 G proteins. Those 10 G proteins will activate maybe 100 cyclic AMP. So each time the signal is amplified. Okay, so it serves as an amplification of the signal. So at the end we will have tons of glycogen phosphorylase active and we have glycogen breakdown. Okay, so this is what happened in time of hunger in the liver. Okay, we're trying to bring the sugar up, so we need to activate the phosphorylase. طيب. Now let us see what happened in the muscle. Okay, so in the muscle we have epinephrine. Actually, epinephrine will work both in the muscle and the liver. Okay, so glucagon work only in the liver, but epinephrine, which is the adrenaline, will work both in the muscle and in the liver. So let's say you are going out and you haven't eaten for several hours and you see a dog coming to attack you and you want to run, your muscles need to work. So which hormone will make sure that you have enough glucose? Adrenaline. Okay, so adrenaline will bind to its beta adrenergic receptor in the muscle and it's going to trigger the activation of the phosphorylase, okay, in order to break glycogen. Okay, so this is what happened and how this degradation is directed by glucagon. Clear? Yes? Okay. So this is written here that we need to amplify the signal. That's why we have a cascade of events. And this is summarized here, okay, the activation. Okay, one last thing. We said the phosphorylase is in 2 forms. The dephosphorylated form, inactive, which is B. The active form, A, is the phosphorylated one. Okay? And we said the phosphorylase kinase will phosphorylate the phosphorylase, making it active. When we don't want to break glycogen, how we will inactivate the phosphorylase, how we will convert back? Yes, so we need to break down the phosphate group from the phosphorylase, and which enzyme is going to do that? Phosphatase. Okay, and it is here, the phosphatase. Okay, so when we are eating, okay, the phosphatase will activate the insulin is released, it will activate the phosphatase. What will the phosphatase do? It will remove the phosphate group and it will change the phosphorylase into its inactive form. Okay? So this is also here. So insulin can activate this other one, the protein phosphatase 1, which is going to remove the phosphate group from the phosphorylase kinase, making it inactive. Okay, so it's all written here, and this is the summary. Okay, so synthase is activated by insulin in the liver and the muscle. It's inhibited by glucagon and epinephrine in the liver and epinephrine only in the muscle. Okay, so glycogen synthase is okay. So this is, we said glycogen phosphorylase is active when phosphorylated. Glycogen synthase is the opposite. Okay, the glycogen synthase is inactive if phosphorylated. So let us look at here. Okay, so when we want to make glycogen, so when do we make glycogen? Yes, so when we have excess food, okay, insulin is secreted, it will
Dephosphorylate that synthase.
it will no. What will happen here? Glycogen synthase B is inactive when phosphorylated, right? Glycogen synthase is inactive when phosphorylated, so it's the opposite of glycogen phosphorylase. So to make it active, we need to remove the phosphate group. Who's going to remove the phosphate group? The phosphatase. So insulin will activate the phosphatase, removing the phosphate group from the synthase to make it active, and therefore this is when we store glycogen, or we make glycogen. So I repeat, when we are well fed, insulin is secreted, insulin will activate the phosphatase will remove the phosphate group from the synthase in order to make it active, because glycogen synthase doesn't like the phosphate group, so we need to remove the phosphate group to make it active. Okay, so it's the opposite of the phosphorylase. The phosphorylase need to be phosphorylated to be active. The synthase need to be dephosphorylated to be active. Okay, and to remove the phosphate group, we need to activate the phosphatase, and this is done by insulin. Okay, now we come to the disease, and it's all summarized in this one slide. Okay, so we call them glycogen storage disease, and they are caused by deficiencies of enzymes related, or enzymes which are needed in the glycogen synthesis or degradation. So we have all these, how many? 3, 4, 5, 6 diseases. Okay, and these are the name of the deficient enzyme. So we have deficiency in the glucose 6-phosphatase, and this is, present where?
In the liver.
In the liver only, not in the muscle. Okay? And then the phosphatase, the glucose 6-phosphatase. Okay, now we're talking about different phosphatase. Now we're talking about glucose 6-phosphatase, the enzyme needed to remove the phosphate from glucose in order to make it free, right? We said the muscle don't have that enzyme because they want all the glucose for themselves. Only the liver have that enzyme, glucose 6-phosphatase enzyme. Okay, so this disease will, is affecting the liver enzyme. Then we have this enzyme, and they put it here, but it's not an enzyme in the glycogen metabolism. But what will happen, when this enzyme is deficient, it's called lysosomal alpha-1,4-glucosidase. This enzyme will, when it's deficient, it will lead to glycogen-like material in the inclusion body. So we will have glycogen material deposited inside the cells, and this is a very lethal disease because the baby will die by 2 years. Okay, but because they have glycogen-like materials, that's why they included it here. But all the other enzymes, they are involved in glycogen metabolism. Right. Then we have a disease in the glycogen debranching enzyme, a deficiency in the debranching enzyme. We have a deficiency in the branching enzyme, so debranching or branching. Then we have a deficiency in the muscle glycogen phosphorylase, the enzyme needed to break the glycogen in the muscle. We also call it myophosphorylase, myo for the muscle. And then we have a deficiency in the liver glycogen phosphorylase. Okay? So how we are going to remember this disease, and I will give you an acronym for these four. You should remember one on its own. This is the most common disease. It's called von Gerke, after the name of the doctor that discovered it. So this is the disease where you have severe hypoglycemia. Why severe hypoglycemia?
Because it's stored.
Because
it's not free to go out.
Yes. So any glucose in the liver is kept in the liver. It will not be freed, okay? And the liver, its function is to regulate the blood sugar. If we cannot free that blood sugar to the blood, if it's kept in the liver, then we will have severe hypoglycemia. Lactic acidosis, because we need excess energy now, we are depending only on pyruvate to lactate to make some ATP. And there is hepatomegaly. What does hepatomegaly? Enlargement of the liver, because that glucose is trapped in the liver, it will enlarge the liver. Also, there is hyperlipidemia, so they have excess lipid in the body. They have hyperuricemia, we'll study this in mole 2. They have elevated uric acid, okay? Uric acid, we'll study this in mole 2. Short stature, so the baby is short. Doll-like faces, the face is like a doll. You know the doll? Okay. Protruding abdomen, because the liver is enlarged, the abdomen will protrude in the bottom. Emaciated extremities. What does emaciated mean? Very thin. Okay? So the hand and the leg are very thin. They are emaciated. So this is what the baby look like. Okay? So he has a doll-like face, protruding abdomen. Okay, so this picture is for von Gerke, okay, and this picture is for Pompe disease. Okay, don't confuse them. So that's why I want to alter the PowerPoint. So this picture is for the von Gerke. So they have a deficiency in glucose 6-phosphatase, and this is the manifestation, and they die if they are not given glucose. So they need to give them glucose continuously, especially when they are not fed, okay? Because when they are fed, they're fine, but when they are not fed, they need to be given a glucose in the night, okay? So this is, and then when they are grown up, they need to have frequent meals and snacks, because they can't store glycogen. Or they store glycogen, but they cannot release that stored glucose. Right, so this is von Gerke. The second disease is the Pompe disease. So this is, we said we have this enzyme, alpha-1,4. Where is it? The von Gerke, the Pompe disease. This slide, Anha. Lysosomal alpha-1,4 glucosidase. I think there is a slide. Yes, so this one, Pompe, the name of the scientist. So it's different because we don't have an enzyme that is missing from the glycogen metabolism, but the enzyme is inside the lysosome, and it's responsible for digesting glycogen-like material that accumulate in the endosomes. So it is more similar to disease that you'll study later called Tay-Sachs or eye cell disease, where we have some indigestible material accumulating in inclusion body. So, but in Pompe it's more severe, and when it starts so it's infantile onset, so it starts at a low, in the small babies, they will have massive cardiomegaly. They don't know why, but the heart is enlarged, and the baby will die before they reach the age of 2. Okay, so this is Pompe disease. Now we have the other 4. Okay, how are we going to remember them? Remember them in couples. So we have these 2 diseases. So we have Anderson, that will have caused by a deficiency in the branching. So let's remember A, B. Okay? Anderson is caused by deficiency in the branching enzyme. You know the branching enzyme that Dr. Ahmed talked to you about? Okay. And then Cori is caused by deficiency in the D branching. So how we are going to remember? CD. So A, B, C, D. Okay? In these two diseases, what you will see abnormal glycogen structure because the branching will add the branches, the debranching remove the branches. So in the clinical manifestation, you will see abnormal branches. Okay, in the branching, if you have a deficiency in the branching, you will see very few branches because you can't add the branches. In the deficiency in the debranching, you are not going to be able to remove that last glucose at the branch. So you're going to have short outer branch and you will have single glucose residue at the outer branch because you cannot cut that last branch because the debranching enzyme is missing. Okay? So this is regarding the glycogen structure. Okay, what about the clinical manifestation? Okay, so is this my phone? I remember putting it on silent. It is on silent. What is this? No, it's a call, and the phone is on silent. And it's a new phone. Don't trust Apple. Okay. So this is, we said the branching. We have at the Anderson, so A, B, C, D. What are the clinical manifestation? In the Cori disease, we have mild hypoglycemia, so it's not going really to affect the blood sugar, but they have liver enlargement because we cannot cut that glucose. Here they have other clinical manifestation, but for you, for our course, just remember the difference in the different the abnormality in the glycogen structure. Okay, what about these last two? How are you going to remember them? So we have McArdle, where we have the deficiency in the muscle glycogen phosphorylase. And the HERS, there is a deficiency in the hepatic. So how we are going to remember them? Yes. So M, McArdle, deficiency in the muscle glycogen phosphorylase. H, HERS, deficiency in the hepatic glycogen phosphorylase. Because we have here deficiency in the muscle, we are going to have symptoms in the muscle. Okay? So the patient will have muscle cramps and weakness on exercise. Whereas here, because we have a deficiency in the liver, we are going to have hypoglycemia, but it is mild, okay, and hepatomegaly. So this is, remember, any symptoms that affect muscle enzymes will lead to a problem with the muscles, like cramping, weakness, fatigue. Any enzymes that affect a liver enzyme will lead to hypoglycemia, okay, because the liver is storing that glycogen to regulate the hypoglycemia. The muscle is storing that glycogen in order to be able to use it to contract the muscle, to move those muscles, okay? So this is summarized in here, the disease. This is the McArdle. So they have exercise intolerance, muscle cramping, myoglobinuria. What is myoglobinuria? They will have the myoglobin in the urine, okay, because there will be breakdown of the muscle tissues, so myoglobin will be released in the urine. Okay, they will have recovery after 10 to 15 minutes of exercise. So the problem is the initial phase of exercise, but after that, they will recover after 15 minutes. Okay, hepatic or HERS. Okay, it is a mild disease compared to von Kerke. Why it's milder than von Kerke? They both affect a liver enzyme. Because the problem is not in phosphatase, the problem is not releasing the sugar, the problem is what? Is releasing the glycogen. But what is the other source of glucose? Gluconeogenesis, okay? Von Kerke, even in gluconeogenesis, any glucose made in the liver cannot be released. Okay, because they don't have the phosphatase. Remember, the phosphatase is needed to remove any glucose in the sugar. So, any glucose in the liver, we need to dephosphorylate the glucose to release it. So that's why the von Kerke has more severe hypoglycemia, because the liver cannot regulate the blood sugar by gluconeogenesis or by glycogenolysis. And this one, the Her's disease, it's only the problem is with the phosphorylase. So we cannot use the blood sugar that is stored, but we can use the gluconeogenesis sugar. We can regulate blood sugar by gluconeogenesis. Okay, so that's it for today. This is a summary of the regulation, and this is a case that you can read at home, and I put for you some animation. Thank you for your attention. I will modify the PowerPoint a little bit, and I will post it by tomorrow morning. Okay, thank you.